Welcome back to this module Review of Caches. In this lesson I will present some useful equations for set associative caches. In my opinion, you don't have to memorize them by heart, but you should be able to derive and apply them. In this lesson I showed you some equations for a direct map caches. These equations relatively easy translate to equations for a set associative cache. The block address is as before given by the byte address integer divided by the number of bytes per block. The cache index is given by the block address modulo the number of sets. If we have a direct map cache, the number of sets is equal to the number of blocks, and block address modulo the number of blocks was the equation we use for a direct map cache. In a fully associative cache, the number of sets is 1. That means the cache index is always 0, and therefore usually we don't mention it anymore. And the tag is now given by block address divided by the number of sets. This gives us another equation. The cache size, meaning the cache capacity, is given by the number of sets, which is the number of lines in our cache, times the number of ways, which is kind of the number of data columns we find in the cache, also 2 in this example of a 4 block cache, times the number of bytes per block. This picture here, this figure here, shows a 4-way set associative cache. Right? To find if a block is contained in this cache, we index the cache using some bits from the requested address. We use 8-bit, that means we have 2 to the power of 8, 256 sets. For each of these cache blocks has a tag. And in parallel we compare the tag to the tag of the requested memory block up here. If either of them and only one of them can match, if either of them match and the valid bit is set, then we have a hit indicated by this large OR gate here. And this multiplexer is needed to select the right word, the right block from the 4 that were given to us. Some questions regarding this figure. How can we see what the block size is? Well, the block size, the last 2 bits are not used to index the cache. That indicates that the block size is 2 to the power of 2 is 4 byte equals 1 word. And what is the size of this cache? Which is equal to the number of sets times the number of ways times the size of 1 block. One more time, this cache capacity equation. If we say cache size, we usually mean how much data can the cache contain. So it is about the cache capacity, right? A lot of questions ask me, do I need to memorize this equation by heart? My answer is no. No, but you should be able to reproduce it. And to give them a hint how to reproduce, I always show this figure. You know what the size of this table is, right? It shows that the number of sets is 8, the number of rows. The number of ways is 4, the number of columns. And the block size equals the bytes per block. So the entire size of this matrix is given by the number of sets times the number of ways, also called associativity of the cache, times the bytes per block. Here's an example for the instruction cache of the Intel Core i7, which is a very recent processor from Intel. Its size is 32 kilobyte. It has a block size of 64 bytes. The associativity, or the number of ways, is 4. It's a 4-way set associative. And the address length is 48-bit. Now the question is, how long is the index in bits? And how long is the tag in bits? Give Given all the information I told you, these questions should be answered relatively easy. First, we know the cache size equation, number of sets times the number of ways times the bytes per block. The cache size is given, the number of ways is given, 4, because it's 4-way set associative, and the number of bytes per block is given because it's 64, it's the block size. So we can calculate this, we can substitute these numbers in this equation. We can divide 32 kilobyte by 4 times 64. This gives us 128, which equals 2 to the power of 7. That means the length of the index must be 7 bits. Regarding the second question, how long is the tag in bits? We must know this equation. The tag length is given by the address length minus the length of the index minus the offset, the block offset length. All this information is available somehow in all these equations. The block size is 64 and 2 to the power of the block offset length must be the block size, so the block offset length equals 6. We know the address length is given here as 48-bit. So the tag length is 48 minus 7 bits for the index minus 6 bits for the block offset equals 35. This brings us to a next question. Which block will be replaced if all blocks in a set are occupied? I didn't bring up this question when the last lesson when I discussed direct map caches, because basically there is no choice for a direct map cache. If a block maps to the same cache block as another in a set, then we need to replace the block that is already present. Now, if we have set associative caches, we can replace any of the blocks in the set. What are usual replacement algorithms for this? One possibility is to replace a random block in the set, the random strategy. Another possibility is first in, first out, FIFO, which tells us that we should replace the block that entered the cache first, which has been in the cache for the longest time. And what is very often used is LRU, or an abbreviation of LRU. LRU tells us that we should replace the block that has not been accessed for the longest time. And we have the optimal algorithm, which tells us to replace the block that will not be used for the longest time. Why don't we implement the optimal algorithm in our in our current computer system? Well, we need to have knowledge of the future. So the optimal algorithm is only a good indication of how far we can get if we have perfect knowledge of the future. It's a limit on the performance we can get. This completes this lesson. Thank you for watching. In the next lesson, I will describe how employing multi-level caches can reduce the miss penalty. Stay tuned.